I apologize for not getting the exams done, but I still have makeups outstanding. So hopefully I'll give them back to you Monday when we get back. Grades will be posted as soon as the exams are completed, but the actual return will happen after I give the makeup. So I want to continue our discussion of analysis of variation. We did single factor, we did two factor with single observation. Now I want to talk about two factor with replication. So that with replication part. What does that mean? Well, we have our two factors. We have the A option, the B option, the rows and the columns in our data. So I have choices here, choices here. In our previous setup, we had one number for each of these combinations. So right here, factor A1 with factor B1, there was one number right there. I think the example we did on Wednesday was drivers going to hotels, right? And there was one time for each combination of driver and hotel. Well, now I want to take multiple observations per treatment. So instead of a single number there, I've got, I don't know, 3, 4, 7, however many. Ideally, I would like to have the same number of observations per factor combination. If I have the same number of observations per treatment, then we're going to call this balanced data. There are ways to deal with balancing your data if it isn't balanced already, provided you have at least more than one reading per treatment combination of factors, then we can adjust our balanced data in several, our unbalanced data to be balanced data in several different ways. We could reduce each collection of data to a single value by taking its collective mean. We could reduce each collection of data to the smallest number of observations per cell. Like if there were at least 3 in every one, we could say, oh, well, we'll put the stuff in order and we'll trim it down to 3 per cell and balance the data that way. There are drawbacks and options that allow you to increase your data by repeatedly sampling a cell. So maybe you only have 10 observations, but you really wanted 12. You could throw all 10 in a hat, shake them up and pull out 2 and use those twice. Something that has this is called an ANOVA with replication, which means I can test for more things. Not only can I test for the effect caused by factor A and the effect caused by factor B, but I can say within this treatment, within this combination, A1 and B1, is there variation there that is due to some interaction between A1 and B1? Maybe driver 3 knows the route to hotel 2 better because he happens to live on that route and he knows exactly where the cops are and he knows where to speed and where not to. So maybe there's another correlative behavior that allows me to describe something called an interaction effect. So for each A and each B, we'll get a main effect. And then we'll be able to say, does AJ, I promise I'll write this correctly at some point, AJBK have some effect that is specific to it interacting in that little collection in that cell, that pile of data. So remember, the main effect would tell me, yes, the choice of A, the choice of driver, makes a difference. The main effect for B would tell me the choice of hotel we are going to makes a difference. The interaction effect would say, is there something specific about this driver and this hotel that makes that one vary more? And again, I'm hoping that all of these effects are what? My null hypothesis. Almost. That the effects are zero and that all of the results are equal. Right. So really my null hypothesis is that the AJ effect is zero. The BK effect is zero. And the combination effect is zero. In other words, there's no difference in average that depends on A. There's no difference in average that depends on B. And there's no difference in average that depends on the combination thereof. The average across each row is the same. The average across each column is the same. This last one is double indexed. The average within each combination is the same. So these are my null hypotheses. That there's no effect due to any of these choices. What's our alternate hypothesis then?
That all of them are not.
I need to say that a little more carefully. It's not that they're all not equal. At least one is different. Instead of all not equal, they're not all equal. Again, this is where English and math speak are different. But at least one of them is different. Now, depending on which way we write the null hypothesis, we can then write the alternate hypothesis in two different ways. We can either write it as all of the factor contributions, the effects, are zero, are not zero, or we can write at least one is non-zero, and at least one mean is different. Again, I'm going to do a crap ton of distance measuring, and I'm going to do this giant calculation with sums of squares of how far away from the average is each data point. Does it matter whether I go left to right or up and down in terms of the rows or the columns? And I'm going to end up doing 3 F-tests. I'm going to do an F-test on A, I'm going to do an F-test on B, and I'm going to do an F-test on the interaction and see if the variation can be nailed down specifically to one or more of these. There is a large discussion of what the calculation actually looks like on page 436. Trust me, it sucks. I never in my entire life have done this by hand, ever. I'm not going to start now, but let's see if we can make it make sense based on our setting. Portfolio analysis. I have here 3 years of data looking at stock portfolio types. We have 4 different portfolios. We have 3 years of data. We have 5 different stocks within each portfolio. And we've measured their volatility. In this case, we're using the coefficient of variation. I remember coefficient of variation. How do we get coefficient of variation again? That was descriptive statistics. That's all the way back to exam 1. You should look in your notes. Chapter 4. Exactly. I take the standard deviation, I divide it by the average, and I multiply by 100 to give it as a percentage. So this set of 2007 stocks in the health portfolio had those coefficients of variation. In 2007, in 2009, oh, there was a little bit more variation in 2009, went back down in 2011. So I can now ask, is there a marked difference in the variation by portfolio type or by year? Is there some interaction that makes one year and type substantially different than the rest? Is one of these boxes not like the other? Or is one row not like another? Or is one column not like the other? So I'm really looking at 3 different analyses here. Again, I'm not doing this by hand. All of this data is available to me in our Canvas page in the set of examples we created for class. Boom. Here, oh, see, now this is where I get to be pissed off. You'll notice in the book, it said 9, 7, 9, and 11. And here on the spreadsheet, it says 17, 18, and 19. What happened? Somebody updated the file and forgot to update the textbook. Whoops. If you've got the electronic version of the book, I'll bet the electronic version of the book matches. No, the e-version of the book still sucks. Oh, well, they just screwed up and didn't make a typo change. I'll live with it. I want to do this analysis. What I could do before I do anything else is I could go by columns or by rows, and I could graph these. Remember, we're looking for interaction effects, right? So I could say, let's make a chart. By row, I had 3 years. Here are 3 rows, 4 portfolio types. There are 4 dots in each color here. And I can say, hey, by row, based on the year, was there an oddball thing where one of the columns is substantially different? If these are roughly parallel, then I would say no, it probably isn't. When interaction gets higher, though, and I see, hey, maybe something was odd out of one of these, then these paths start to cross more. So in this case, I see that odd behavior in the retail sector, where this third out of fourth year, sorry, this third portfolio, health, energy, retail. Oh, retail. Retail gave me something different that year than it did the other years. I could do it the other way and go across the years. Again, I see that green one crossing stuff, but now this green one represents the retail, but it's now by year. That's why we have 4, because I've got each portfolio being aligned. But we clearly see that that middle year was higher most of the time. First one was a little lower than the middle, but then that third year, 2019 was a bad year, right? We all know why 2019 was a bad year, right? Oh, okay, all sorts of stock tanks because of COVID. But there we go. We see a comparison. Let's actually run the numbers. I'm going to go to my data pile. Data analysis. I want to do an ANOVA with replication, not without, because I've got multiple pieces of data per cell, and they are balanced this time. I've got 5 observations for each year and portfolio type. This is balanced data. So it says, where's your data? Right here. Click. Rows per sample. Oh, there are 5 rows in each sample. I'm doing alpha 0.05, and I wanted to push this into a new worksheet. Boot. A lot of math just happened behind the scenes. And here at the top, I have 4 summary sets of data. I have it across each year, and I have it by each column. I also have a total per column here. And then down here, I have an ANOVA. So now I can ask. Please notice it didn't bring the labels with it, which bugs me a little bit. It didn't tell me rows, columns, which one is which. I have to know from my data that rows here are the year, columns are the sector, what type of portfolio I've got. So here, this is about the rows. Does my choice of row matter? Do I accept my null hypothesis or do I reject it? If I accept it, then it means there's no difference between the rows. What year it is made no difference here. Mm-hmm.
So it would matter. But looking at the people, confused because are bigger than our 0.05.
This is a difficulty in the way that p-value is expressed. Because you think 0.005 and then you see 1.3, right? But that e minus 14 at the end is scientific notation. And that means that's multiplied by 10 to the negative 14th. So that is really 0.000000000000001. That's a lot smaller than 0.05. So yes, I agree with you. That F value is a lot bigger than that critical value, and that means we should reject. The p-value should be really small then, and it really is very small. It just doesn't appear that way because they've written it in scientific notation. So I now know that the year mattered. What about the type of portfolio? Why so, Emily?
Same, the, small, the 0.05 and the, F is greater than the.
Again, we're doing a right tail test. And that F critical is 2.8 and our F value is 5.5. That's bigger. That P value is 0.0025. We wanted 0.05. That's a 20th of the size. That's much smaller. Reject my null hypothesis. So which year it was matters. Which type of portfolio it was matters. Is there some interaction between these two that says one of these is particularly egregious? Yes. Our interaction effect here also says the same thing. An F value of 4.96 against an F critical of 2.3, a p-value of 0.0005. There's something clearly interacting between year and portfolio type. Go together and say, oh, something's specifically unusual about one of these. I can then go back up here and start to say which one of these has the largest differential, has the most specific. Now I could go do individual F tests. And I could say, which one of these do I think is the outlier? To me, that's where these plots come into play. And I say, oh, I think the outlier is right there. It's the retail one in 2019 that did something unusual from everything else. If I had managed to cash out retail in 2019, I would have actually been ahead. Consider that comparison between health and energy and leisure makes a lot of sense. Health stocks didn't do much better in 2019 because everybody's panicked. Energy stocks, everybody stayed home and did a whole bunch of work from home, and energy usage in terms of gasoline used cratered. Nobody was driving anywhere. Nobody was flying anywhere. Cratered out the stocks. Leisure activities, I'm stuck at home. I did a whole bunch of Netflix. That's not exactly the same sort of leisure budget that most people had. But retail sales, Grubhub went through the roof. Uber Eats and Amazon deliveries started going way up. If I'd cashed out 2019 in retail, I would have made money. I had no foresight. I don't play the market like this. I'm broke anyway. Doesn't help me. But I can clearly see the one outlier is that one. I could then do a specific F test for that particular one against the global behavior, like we see here. Questions? The thing I need is to understand, what am I testing? That's why I keep asking you, what are the null hypotheses? What are the alternate hypotheses? What is the question being asked before I can decide whether or not something matters? I need to know what I'm testing before I run this, or the numbers come up and I'm like, now what does it mean? Churning out the numbers is the easy part. I pushed 3 buttons. Interpreting it is what's going to make me a valuable employee to my boss. Questions? Close. Okay. Here's another one. Market research firm puts out a new shampoo. We have 4 age groups: youth, college, adult, senior, in 4 different regions of the country. And we ask customer satisfaction surveys. Does your customer satisfaction depend on where you live or how old you are for this shampoo? Notice again, we've got 5 observations per group. I don't know, maybe they did 5 different focus groups, and this is the average from each one rather than 5 individual people. I don't know how they did this, but we have, according to this, there are 5 people in each panel, so maybe this is 5 individuals. So, again, my question, does where I live matter? Does how old am I matter for this product? Grab this data file, or if you've got it, problem number 27 off our Canvas page. Grab your computers, let's pull this sucker down. Here we are, module number 4, in-class examples, chapter 11, number 27, satisfaction. Right here. Here's our data set, stolen right from the Excel spreadsheet. Run me the 2-factor replication ANOVA. Yes, our alpha is still 5%, yes. That's a default setting unless I'm really got a reason to look for something either more stringent or looser. Almost every ANOVA on the face of the planet is run at 5%. I wish I had a better reason other than that seems to be what everybody accepts. A large amount of calculation happens behind the scene. Summary information off the top of my head isn't going to give me a lot. So I'm going to go down here to our actual ANOVA results, stretch out column 1 so I can see everything more clearly. Rows, our sample discussion. Does the age group make a difference? Apparently, a lot of a difference. This p-value is tiny, F is much larger than F crit. This is a big difference. So either college students love this, youth love this, and older people hate it, or vice versa, somewhere in there, the satisfaction is clearly age-driven. That is a strong result. How about region? Does where I'm located make a difference? Because
Greater than 5%, and your F crit is bigger than your F value.
my F calculated value is 0.055 and my F critical value is 2.7. No, that's definitely not significant. P-value of 0.65 when I want 0.05 or smaller, which means the effect we see is nationwide. It's not area specific. So maybe that northeast cold wind and that southern beach lifestyle doesn't make a difference for this shampoo. I don't know. You buy this particular shampoo, go swimming in the ocean, and your hair turns green. I cannot tell you the number of times people in Florida had green hair because their blonde hair dye interacted with the chlorine in a pool. Grew up in Miami, saw it a lot. Interaction. Is there an interaction between region and age? Is there one particular region-age combo that stands out? Felix? Aha.
Yes. Yeah, it's small, that's right.
0.0009 is definitely smaller than 0.05. Yeah, that makes sense. There is some interaction here. There's some interaction between age and region. So it may very well be that the youth in the Northeast or the college student in the Northwest, there might be something going on there. I don't know which ones yet, but there is some interaction. Now, as I look at the p-values, the bigger that p-value away from 0.05, the less effect I've got. The smaller the p-value away from 0.05, the more of an effect I've got. So this very small p-value here, escape here on my rows tells me that's a really strong effect. The age of my individual matters, not just a little, but quite a bit. Let's look at the interaction plots because we decided there is some interaction. So I'm going to graph this both by region and by age. So here, I'm graphing the average from each across the region. So you'll notice that my column designations here, Northeast, Southeast, Midwest, and West, but then I've got a row for the blue, a row for the red. Those are ages. So youth, college, adult, senior. It looks here like there's a lot of crossing over of these lines. That tells me there is an interaction here. I see it in this reaction between adult and senior here. I see this big cross of adult over youth and senior in the Midwest. Yeah, there's some interaction here. If I go the other way, again, there's a substantial amount of crossing over. Here, the colors indicate which region I'm in. And the dots are youth, college, adult, and senior left to right. If interaction is low, these plots are parallel. The further apart they are, the more that effect matters. Remember, we said region didn't matter very much? Notice how close all these lines are? But there is still some crossing over. So there's some interaction here, in spite of the fact that this effect isn't big. The closer together the curves are, the less that factor matters. Notice how close these are. Notice how much further apart these are by comparison to one another. My interactivity now says, yeah, it looks like age matters a lot more than region, because these plots are further apart. The other ones are very close together. I could now do a pairwise t-test. The problem is that I have 16 different options here. Remember, here's my data set. There are 16 different cells here. If I think this is the weird one, I want to check it against some of the others, I'd go back to that picture and I'd say, okay, who did the biggest cross where? That's, I think, my outlier. Let me do a t-test with that one against one other, or against the global average, either by row or by column, depending on which way I think that matters more. Since we decided that age mattered more than region, I'd probably do it against the row averages. And again, I have the row averages in my summary data up here. There are my row informations right there. So I could take the one oddball, which we thought was here, adult Midwest, adult Midwest, and I could take that sum and that average and run a t-test against this set of data for youth, against this set of data for college. I could run it against the other set of data just within here, but I already know that the region doesn't matter, so that doesn't help me very much. And I could run it here. I could run it just within the columns for the Midwest and run 3 t-tests. Adult against senior, adult against college, adult against youth, to see if this in fact is limited just to adult and how significant that is. I could run now single factor ANOVA. There is a way to do a combined test to get more specifics on the interactions. There's something called a Tukey test, T-U-K-E-Y, it's a person. And it's a t-test, but it does a lot of t-tests at the same time, like our ANOVA does. It is not used very frequently. There are other methods for pulling out interactions better, but they really come from the idea of looking at the effect we were getting at. I need to go back and be a little more theoretical for a second. When I was talking about the idea that there really wouldn't be any effect from A or B or some combination thereof, what I was really hoping was that the data could be predicted by some overall giant average. And there might be a little bit of an effect from A, and there might be a little bit of an effect from B, and there might be some combo effect, and then there might be some random error. Our null hypothesis said that all 3 of these effects would be 0. And in our case, the example we just did, we said the rows mattered. This effect was not 0. The interactions mattered. This effect was not 0. But this effect, this was effectively 0. This really didn't do anything. We rejected the null hypothesis there. Oh, sorry, here and here. We accepted it here, failed to reject. Okay. This is, in effect, the equation of a line. This number is this one plus some effect multiplied by my row, multiplied by my column. So that's like the equation of a straight line. We had some number that we were adding to, and we had some number that was affected by our items. This AJBK effects, they behave like our slope idea. So if I could actually make a linear equation to show the interaction, not just that there is an effect, but how big is that effect? I just said age mattered. Satisfaction with this shampoo mattered by age. Maybe I'll be able to say, you know, the older someone gets, their satisfaction goes down by this many points per year of age. And then I could focus my marketing for this shampoo to the group that would like it the most. But that would be a linear effect. I've seen this before. I know I've seen this. If I can do this and actually quantify the difference in effect, not just there is an effect, which is all ANOVA tells me, there is an effect. But if I can figure out how much of an effect, then I can make predictions. And I can make decisions in a better way because I have this information. This is the idea behind the next chapter. I want to take this variance idea and quantify it and measure how much of a difference does this thing make. I'm going to start easy though. I'm not going to start with 2-factor. I'm going to start with 1-factor. For example, the following is in no means designed to put pressure on any of you. Can I quantify score on an exam versus number of hours studied? I don't know. I would hope so. I would hope that the more you study, the better you do, but I don't know. So I'm going to do a survey. Now, we got finals in a couple of weeks. Let's sit down and let's start asking people, how many hours are you going to study for this exam? And then at the exam, I will ask them, how many hours did you study? The problem is self-reporting data, people lie out their asses, but I'll take their word for it for now. And then I'll be able to say, hey, is there variation based on how much studying they did versus where the grades are? For the past 15 years, I've been collecting this exact kind of data on attendance. Does coming to class make your grade go up? I've had students who have shown up exactly 5 times in a semester. Showed up for the first day, each exam, and the final, and that was it. I never saw the kid other than that. First semester he did that, he got a B. Next semester he got a B minus. Semester after he got a C. It wasn't helping him in the long run, but it happens. I wanted to track this. So I take attendance for exactly that reason. They attend because they make it, but I now have a correlative behavior. I have a correlative behavior. Where did we do correlations? Where did I see something about correlations? We talked about correlations and probability, yeah. And we looked at them in the light of what kind of pictures? We looked at them in light of scatter plots, looking at related pieces of data. We plotted them and then we tried to draw. Aha. I'm going to try and figure out how to quantify this sort of variation with a line through my data. But that is a week from today. I hope you all enjoy your Thanksgiving break. I will see you then. Have a wonderful day. This chapter is now over. This assignment is therefore due a week from Wednesday, the Wednesday after we get back.